In this video, we will be going over complex numbers. We have seen throughout the past videos that the square root of a negative number does not exist in the real number system because there is no real number when squared that will result in a negative number. For example, the square root of -4 is not a real number because there is no real number whose square equals -4. Well, the square root of negative numbers do exist, however, under another system of numbers called complex numbers. And before we define what a complex number is, we must define the number I. The number I is called an imaginary number, and it is defined as the square root of -1. Therefore, squaring both sides gives us I squared equals -1. And it's going to be very important that we understand these two facts about imaginary numbers, as we will be using them often. Now let's define what a complex number is. So a complex number is a number of the form a plus bi, where a and b are real numbers. A is called the real part, and b is called the imaginary part, due to it being multiplied by I. And the following table will list some examples of complex numbers and their real and imaginary parts. The first complex number, we have the real part being -5 and the imaginary part as 2. For the next complex number, the real part is 1/3 and the imaginary part is -7. For the next one, the real part is 0 and the imaginary part is 8. And then for 4, the real part is just 4 and the imaginary part is 0. And note for the complex number 8i that it can be written in the form a plus bi as 0 plus 8i. And likewise, besides 4 being a real number, it can also be considered a complex number because it can be written as 4 plus 0i. Therefore, since all real numbers a can be written in the form a plus 0i, we also consider all real numbers as complex numbers. However, the reverse is not true. All complex numbers are not real numbers. Okay, so now let's try some examples. We want to simplify the following radical. And since we have a negative number in our square root, this will not equal a real number. We will instead have a complex number as our simplified expression. So now that we've defined the imaginary I as square root of -1, we can rewrite this radical as the square root of -1 times 9. And using the product property, we can write the product of two radicals, square root of -1 times the square root of 9. The square root of -1 can be rewritten as the imaginary number I, and the square root of 9 is 3. Therefore, the square root of -9 simplifies to I times 3, which is the same as 3i. For the next example, since we have a negative number in our square root, this will also not equal a real number. We're going to get a complex number again. So we can rewrite the expression as the square root of -1 times 7 and use the product rule. The square root of -1 can be rewritten as I, and the square root of 7 is already simplified, so we can leave it as a radical. And our original expression simplifies to I times the square root of 7. So for this answer, let's keep it written so that the imaginary number I is written in front of the radical, just to be clear that the I is not written under the radical. It will be good practice to write the I before the radicals. For the square root of -12, we can rewrite this as the square root of -1 times 12, which equals the square root of -1 times square root of 12, and rewrite the square root of -1 as I, and it looks like we can simplify the square root of 12, since 12 has a perfect square factor of 4. This will then simplify to I times 2 times square root 3, which is the same as 2i times the square root 3. So we're going to need to be careful when multiplying and dividing square roots with negative radicands. It is important to write each radical in terms of I first. We must also keep in mind that I squared is the same thing as -1. So for example, if we are multiplying the square root of -8 times the square root of -2, this does not simplify to the square root of 16, which is +4. We first need to write each radical in terms of I before multiplying. So we can write the square root of -8 as I times the square root of 8, and the square root of -2 as I times the square root of 2. And now we can multiply this out. We get I squared times the square root of 16. We replace I squared with -1, and the square root of 16 is 4, and so we get -4 as our answer. So just as we can add, subtract, multiply, and divide real numbers, we can perform all of these operations with complex numbers. Let's begin with adding and subtracting complex numbers. So to add complex numbers, we combine the real parts and combine the imaginary parts. And to subtract complex numbers, we apply the distributive property and combine the real parts and combine the imaginary parts. So for this example, to add these complex numbers, since there is no negative in front of these parentheses, we can rewrite it without the parentheses. And now we combine the real parts, and then combine the imaginary parts, and this will give us 12 plus 5i. To subtract these complex numbers, we first need to distribute this negative across. And now we combine the real parts and combine the imaginary parts. This then gives us 4 plus 5i. So we multiply complex numbers just like we would multiply polynomials. There may be just an additional step, and we must remember to replace I squared with -1. So for example 3, let's multiply. To multiply this, we distribute the 5 across the terms, and this will just give us -10 plus 15i. For the next one, we need to distribute each term from the first binomial to each term in the second binomial. So we have -8 plus 32i minus 3i plus 12i squared. We can combine the imaginary parts and then replace I squared as -1, combine the real parts, and we get -20 plus 29i as our answer. For the next example, again we want to make sure to distribute each term in the first binomial to each term in the second binomial. So we have 36 minus 12i plus 12i minus 4i squared. The imaginary parts cancel out, and we can replace I squared as -1. This will then simplify to 36 plus 4, which is 40. Okay, now let's go over how to divide complex numbers. So recall that in order to simplify 2 over 3 plus square root 5, we would need to eliminate the radical from the denominator. And we do this by multiplying both the numerator and the denominator by its conjugate, 3 minus square root 5. And this eventually gets rid of the radical from the denominator. So we divide complex numbers in the same way. The conjugate of a complex number, a plus bi, is a minus bi, where we just change the sign between the real and the imaginary parts. So to divide complex numbers, we multiply the numerator and the denominator by the conjugate of the denominator, and then we write the quotient in the form a plus bi. So let's try a few examples. So to simplify this, notice that there's technically a radical in the denominator since I is the same as the square root of -1. Therefore, we will need to rationalize the denominator by multiplying by its conjugate. So the conjugate of 4 minus 5i is 4 plus 5i, so we multiply both the numerator and the denominator by this conjugate. we can cancel out the 20i minus 20i and also rewrite I squared as negative 1. And this simplifies to 12 plus 15i over 41. And now we've eliminated the I from the denominator. Since we have to get it in the form a plus bi, we can separate this as two fractions. So we have 12 over 41 plus 15 over 41i. For the next example, again, since we technically have a radical in the denominator, we will have to rationalize this by multiplying both the numerator and the denominator by the conjugate, which is negative 7 minus I. So we multiply the numerator and the denominators across and simplify. So we can combine the imaginary parts, negative 6i plus 14i, and then we can replace I squared as negative 1. The imaginary part 7i minus 7i cancels out, and we also replace I squared as negative 1. And now we can combine the real parts, and we get negative 44 plus 8i over 50. And now we've eliminated the I from the denominator. Since we want to get it in the form a plus bi, we'll now separate this as two fractions, and we can simplify this. So negative 44 and 50 have a 2 in common, so this simplifies to negative 22 over 25. And 8 and 50 also have a 2 in common, so this simplifies to 4 over 25. So now our quotient is negative 22 over 25 plus 4 over 25i.